All right, last part of this one, I want to find and simplify this function y of n, and y of n is basically the difference quotient for f. So this says you're supposed to take f of n plus 2 minus f of n all over 2 and set that fraction up and simplify it, and that is what we're calling y of n. So let's do a little side work. I already rewrote f of n, so I have it here. But just for reference, f of n plus 2 would just plug in an n plus 2 where the n was. So we need to take that f of n plus 2, which is 3 plus 12 divided by n plus 2, minus f of n, 3 plus 12 over n. And be careful about the parentheses there. You need to subtract the entire f of n, not just the 3. And then we'll divide it by 2. So what can we do here? This negative sign is going to distribute, so it's going to be a minus 3 and a minus 12n. So we'll have 3 plus 12 over n plus 2 minus 3 minus 12 over n. The 3's will drop out, so that's really nice. 3's are gone. And then we have that 12 over n plus 2 minus 12 over n. We could deal with the 2 pretty quickly, but I'm going to say for the purposes of this one, just to practice the algebra, let's try and make this a single fraction on top and then deal with that divided by 2. So if we have 12 over n plus 2 minus 12 over n divided by 2. If that wasn't just a 2 sitting on the bottom in particular, I'd love to clear fractions, and there's a really nice trick to clear fractions, and that is basically just to look at those internal denominators that you'd like to get rid of and multiply top and bottom of the big fraction by that. So we'll have an n times n plus 2 over an n times n plus 2, and when we multiply straight across, it does make the denominator messier, so now we have a 2n times n plus 2 in the bottom, but it will clean up the numerator a lot. So we're distributing this in, so it's basically going to be this times n and n plus 2, and then this one times n and n plus 2. So in that first fraction, we get to cancel out the n plus 2's. Just make sure that you multiply both fractions. If you cancel this and you don't end up multiplying the other one by the whole thing, it's going to be wrong. In that second multiplication, we get to cancel the n's. So we're just left with the 12 and the n plus 2. And now all of a sudden, I don't have a complex fraction. So let's see, I'm almost done. I have 12n minus 12n minus 24. So again, lots of distributing. Distributing is something that you might not have had to think very carefully about before, but you're going to have to be really careful with it here. 12n minus 12n is 0, so we can get rid of that. We'll just be left with that negative 24 in the top. And so just because I've written this so many times, I'm going to skip one rewrite and say I'm going to cancel that 2 out. And there will be negative 12 over n times n plus 2. And that is this y of n function. So mostly here, this is just an algebra function notation exercise, but we will look a little bit into what it tells us about rats. So I would say, looking at that final equation, I have no idea. But if I look back up at that first equation, what I'm seeing there is an average rate of change. So just to expand a little, this is the top. The bottom is just a 2, which might look a little weird. But if you think about it this way, if we had n plus 2 minus n, that really would just be 2. Maybe that'll show you the average rate of change again. So that's a change in y over change in x. So it's telling me the average rate of change, and remember this f function was time to complete a trial and which trial you're on. So this is telling me the average rate of change in the time with respect to how many trials you've gotten. In particular, we were supposed to find y of 1. Sorry, I didn't reread my own problem. So let's go ahead and plug that in, but I've already gotten us a head start on the interpreting. So we'll get negative 12 over 1 times 3. So -4. And I'm going to keep that over 1 because I've already kind of established here that what that really is an average rate of change. So we're saying n equals 1. So this would be f of 3 minus f of 1 over 2. Okay, so from trial 1 to trial 3, the time decreased by 4 minutes per trial on average. So that's pretty good, dropping 4 minutes per additional trial on average. If you actually check trials 1, 2, and 3, it might not perfectly go down by 4, but the average overall is that it goes down by 4 minutes per trial. So that's what we're getting there. It is an average rate of change, and I want you to keep watching for those and recognizing them. Okay, I have just one more question, and this is getting very much into calculus thinking. What happens to this y function as n goes to infinity? So remember, y was -12 over n times n plus 2. So if n gets really, really big, we're dividing by a big number multiplied by a very, very slightly bigger number. So it's roughly the square of whatever we're plugging in. So big number times big number. The denominator is huge. When we take a number like 12 or -12 and divide it by a massive number, this is going to go to 0. Dividing by really, really big numbers gives you really, really small numbers. What this is telling me about rats, so this is saying as the rat does more and more and more trials, it's not the time that's decreasing by 0, it's the rate of change in time that's decreasing to 0. So it's saying that basically the rat quits improving. It's improving by tiny, 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 basically 0. As we do more and more and more trials. And if you think back to our graph where we had that asymptote at 3, hopefully that'll make some sense. So the time is decreasing to 3. The rate at which the time is decreasing is going to 0. It's not decreasing anymore. So that's very tricky. We'll get to it. That's like second derivative thinking, but just try and think through that and make sense of it. All right, thanks for watching.